Welcome to dual coding mind mapping for radioactivity. You're going to need 2 pieces of paper and a pen or pencil. The first thing you need to do is to write down exactly what you see on the screen. I'm going to be explaining as you write, and then what you are going to do is relay the information back to yourself or to somebody else as we go through, and I'll explain that at each step. So the first thing you need to do is copy down what you see on the screen, the radioactivity symbol and word. We have our first branch, and here we're talking about atoms, and we need to know the history of atomic structure and the history of the atom diagram. So the first one is Dalton, and his diagram was very, very simple. It was just a solid mass, circular mass, and that's what he thought that an atom looked like. Then came J.J. Thomson, and here we have what we call the plum pudding model. Okay, and here we have a circular circumference with random negative electrons inside. So it thought that it had a massive positive, the whole thing was positive, and it had these negative particles attracted to it. Rutherford then discovered, using the gold foil experiment, that by blasting particles at an atom's nucleus, then there was something in the middle that it bounced off of, and that's how we got the nucleus. There was something there which these particles are attracted to and then were flung off in different directions. We then come to the modern day, and here you can see we have electron shells, we have a nucleus with protons and neutrons inside, and we have energy levels, energy shells with electrons that sit in those different shells. And you can also see that electrons are negatively charged and protons are positively charged. Now the number of protons is equal to the number of electrons. So if there's 11 protons in the nucleus, there will be 11 electrons surrounding that nucleus, orbiting it. Inside the nucleus with the protons, we have neutrons, and they have no charge. So we have an equal amount of charge in each atom, because we have the same amount of protons as we do to electrons, and these are called subatomic particles. Now with this we have something called isotopes, and isotopes are of the same atom, but each time the neutron number increases. Now this allows us to do a number of things. We can do carbon dating with carbon because it has a number of isotopes. It's also why chlorine has a mass number of 35.5, because it has isotopes, and so it takes an average of that mass number. What I'd like you to do now is to pause the video, make sure you've got everything written that you need, and then using your finger trace the diagram and explain as you trace. As you go through, re-explain it. You can explain it to yourself or to somebody else. Once you've done that, restart the video. Our next branch is fluorescence, and this is linked to our isotopes. Okay, now we can have fluorescence because of these electrons jumping these energy shells. When it jumps towards a nucleus, so it can change any energy levels towards the nucleus, it emits energy, and it does this in the form of light, and it does this using the electromagnetic spectrum, and it's how we are able to see fluorescence, such as neon lights or neon face paint. When it jumps back away from the nucleus, it absorbs that energy. Okay, so it's continually absorbing and emitting energy. I'd like you to stop there, re-explain this, tracing it to yourself or to somebody else, and then start the video again once you're finished. Now we have ionisation, and this is how we get radioactivity. Now ionisation is either the gaining or losing of an electron. It's ionic bonding. Okay, and we have an electron which is negatively charged. So if we lose an electron, we end up with an atom that becomes positive, because remember there's the same number of protons as there is electrons. So if we lose an electron, we're losing one of those negatively charged subatomic particles. So if we started with 11, we now have 10. So we have one more positive proton than we do negative electron, and so it would have an overall charge of +1. Now this is called an ion. It becomes an ion because it's become ionized. And so we use this and we display this via the brackets and then the charge at the top of the bracket. And depending on how many electrons are lost or received, that's the number that goes next to the symbol of plus or negative. Now remember, if we gain an electron, then we are becoming negative, because we now have one more negative electron than we do positive proton. So we become a negatively charged ion. I'd like you to pause the video, re-explain this, tracing it with your finger to either somebody else or yourself, and then restart the video once you've finished. Our next branch looks at background radiation, and this is radiation that is around us all the time. We cannot escape background radiation, and there are a number of sources in which this comes from. We have nuclear, food and drink, radon gas, which there is quite a lot in the UK, buildings because of the raw materials they're being made from, and medical supplies. There are some medical supplies which have background radiation. So background radiation, as I said before, is all around us. We cannot escape it. It is always there, but it's at such a low dose that it doesn't affect any of our cells. It doesn't affect us. Now you can detect background radiation using a Geiger counter, and we can measure it by hearing the clicks from the machine. I'd like you to pause the video, trace the diagram with your finger whilst you re-explain what's happening. Our next branch is types of radiation, and here we have alpha, beta and gamma. And alpha is quite a large particle, and it can be stopped by paper. Paper will stop alpha particles from going through. Now an alpha particle can be emitted, and it has 2 protons and 2 neutrons. Now beta is slightly smaller, so it can go through paper, but it can be absorbed by aluminium foil. Now beta decay is where a proton becomes a neutron. So whereas an alpha particle, it loses 2 protons and 2 neutrons, here a proton becomes a neutron. So it changes that mass, or the amount of neutrons and protons, but it doesn't change the mass number. Gamma radiation, this loses energy by a gamma nucleus is rearranged, and this cannot be stopped. It's so small it cannot be stopped by paper or aluminium foil. We have to use lead, and that's why there's a small pencil on the screen, because of lead. Now it's not only lead, we need lead surrounded by concrete. Gamma is very, very good at getting through different surfaces, so we need to lead line it, and we need to have concrete surrounding that lead. Now types of radiation and decay. Now with decay we have something called half-life, and half-life is the amount of time taken for the atom to halve. Okay, so if we had a graph of radiation over time, and if we took the middle of that time, so if it was an hour, we took 30 minutes, and we saw how much radiation was left after 30 minutes, that is 1 half-life. If we then look again, half the 30 is 15, that's 2 half-lives. I'd like you to pause the video, trace with your finger whilst re-explaining to yourself or somebody else, and then restart the video once you've finished. This is our last branch of radioactivity, and this is all about the dangers of radiation. Now here we're looking at how radioactive material or radioactive substances can be dangerous to us, and what happens is we can get something called radiation sickness. Now what this does is it mutates our cells. Now when our cells copy and divide, occasionally we get a mutation where the copying process isn't quite right, and during our genetic coding, one of those sections or one of those letters that is in that code gets copied wrong, and so we have a mutation, a mutated cell. Now that most of the time is okay, but when it comes to radiation, this is not a good thing, and it starts to destroy our cells, because those mutated ones then also copy and make more mutated cells. So radiation sickness is really, really quite nasty and can happen quite quickly. Now we can protect ourselves to an extent with radiation, and in school you would have seen a demonstration of alpha and beta radiation sources, and you would have seen the teacher put on a pair of gloves and use tongs. And you can also use a mask and an apron to protect yourself, and you need to know how to protect yourself when using radioactive materials for your exams. It's generally a question that comes up on safety, so you need to know how to protect yourself, and you can do this again by gloves, tongs, apron, and a mask. Pause the video, retrace your steps using your finger, tracing your diagram whilst explaining to somebody else. What I'd now like you to do is to look at your mind map, and we've got a lot of information on this mind map. There's lots of different symbols, lots of different words that you need to know. So study it for 5 minutes, and then once those 5 minutes are up, take your second sheet of paper and from memory, don't look at the original sheet, write down as much as you possibly can. Now the more times you do this, the more you're going to remember it, the more it's going to stick in your brain, the more you're going to be able to recall later on. So do this every week or every few days to try and get you to remember as much information as possible. Then compare your 2 mind maps that you've completed with your first one and then the one you've completed to see how well you did. Thank you for listening to dual coding mind mapping for radioactivity. Please tune in again for a different unit.